So our first virtual speaker is Konrad Gajewski, who's going to talk about regression models using AI.
Okay, so can you hear me? And does this appear correctly or not?
Yep, we can see everything.
Okay. Okay, so.
Actually, Conrad, if you don't mind just holding on for a second, we're having a slight technical issue here with sound. Are we doing anything with the sound, or? He's coming? Okay. Yeah, okay, Conrad, if you don't mind just holding on for just a minute.
Okay.
It's okay now? Sorry, what? Seems fine? So, Conrad, we're seeing the infinite mirror right now. If you can bring up your presentation again.
Okay, it's there. You can't see it?
I can see you, but I can't see the presentation.
Okay. Oh, let me share screen again. Okay, can you see it now?
Yes.
Okay, is it full screen or should I do something different?
You can make your PowerPoint presentation full screen on your end.
Okay. Now is it okay?
That looks perfect.
Okay.
I think we can go ahead. Right, great.
So should I go?
Yes, please.
Okay, so here's the issue. Linear regression is simple, easy to use method. But when I read the literature, I'm surprised at how often published analyses are simply wrong. And I don't know what word to use here, but I'll give some examples of how people present linear regressions and they're violating the assumptions of the model. Now, this can happen by various methods that I'll talk about, but it's also easy to fix. So here's just some examples from the literature of what I'm talking about. And the uppermost two, you can see they're fitting a linear regression to a curved, what should be a curved relation. And so that means that they really can't tell you what's the significance of the R squared or if the beta parameters are significant. The second graph, for example, and much of my work is from paleoclimate examples, it's harder to see. Perhaps these curves are correct, but perhaps they're not. Here's some other examples, just as a whole series of them. And if you notice on the left-hand side, C, here we have, if you look carefully, you see there's a whole bunch of points around 0. And basically this R, or the regression that they're fitting here, is determined only by those 2 points that are sticking up there. On the right-hand side is something that's quite common today. They're showing several different curves with different colored dots and so on. And this is sort of efficient way of presenting things, but it also makes it difficult for the reader to evaluate the quality of the regressions. Here's some other examples, and on the left-hand side, upper left-hand side, they have a series of regression lines, well, again with colored lines. They're telling you the probabilities of them, so that means that assumes that they haven't violated the assumptions of the model, but it's hard to evaluate. And on the lower and on the right-hand side, this is actually a paper on artificial intelligence applied to some kind of a question. And what you can see is that, in fact, the line that they're, the prediction line, the curve that they're showing does seem to be violating the assumptions of the regression. It doesn't seem to fit properly in the uppermost part of the curve. And just a quick other example, notice on the right-hand side, the upper right-hand side, they have some regression lines there. And you notice that there's this big cloud of red points there around 0. And that regression line seems to be determined only by those few other points there. And just as an example of why this might be important or interesting, on the bottom is from the CBC, where some researchers did, this is in the social sciences, they looked at polling and they said that if the price of gasoline goes up, the approval rate of the president goes down by 0.6% per every 10 cents increase in a gallon of gas. Well, if people are going to determine policy based on these kinds of statistics, this quantification, we want to be sure that the regression that they use to get this is properly done. Now, in linear regression, the assumptions of the model are on the residuals, not on the data. And when you fit a line, well, it's just a mathematical operation and just draws a straight line through the data. However, if you meet the assumptions of the linear model, then you can determine if the explained variance is statistically significant. So you can tell if the model is useful. You can determine if the parameters are statistically different from 0, that is, if the model is needed. And then also you can determine the confidence intervals and so on. So the assumptions of the linear model are on that the residuals have a mean 0, standard deviation E. Residuals are normally distributed and independent and identically distributed. So the procedure for modeling, and this would apply to any kind of modeling that you're doing, you postulate a general class of models. This is from Box and Jenkins. We'll be looking at linear regression. We identify a model that we're going to try to fit. Here we'll just use a simple linear model. And then you estimate the parameters. And this step, number 2, is trivial. You could do this in R, MATLAB, Python, whatever. But the key here, and which is often missing, is the diagnostic checking. Is the model adequate? And that's what I want to talk about today. So I'm going to give you a case study from the literature where, and this has to do with instrument calibration. So in lake and ocean sediments, you want to measure primary production and perhaps climate. And you use chlorophyll products in the sediment to do this. Now, typically, the way to do this is you have to use some, spectroscopy or some method like this, which is extremely complicated, very expensive, and very few people are set up to do it. And this will then give you the units, which would be chlorophyll A, milligrams per gram, or something like that. But what they've used is a remote sensing where you use physical reflectance spectroscopy to do this. This is trivial measurement. You point your instrument at the sediment and you quickly get a whole series of samples. And you quickly get measurements and you had a whole series of samples. But it had to be calibrated. And so there was a series of papers published where they tried to calibrate this method. On the left-hand side, you can just see what it sort of looks like. Basically, that gray area, that's the deviation from something, and it's that area which should be proportional to chlorophyll in the sediments. And on the right-hand side, they show on the y-axis the chemically measured, the actual value, and the remote sensing value on the x-axis, which is in units of area or something like that. Meaningless units, but if you can calibrate this, then you know what the chlorophyll is in the sediments. So here you have the equation, and I just want to point out here, if you look at that and look at those 2 points that are circled on the left-hand side, so I pulled off the data and I've replotted it on the right-hand side. Now you can see sort of going from 0 off to the upper right-hand corner, there is a black line, and that's the fitted line that they used in this paper, and it's just used with all the data. And then what I did was I just started removing points one after the other and just plotting the lines. If you see on just across there, if you remove point 2, which is in blue and labeled there, you get the blue line, and it looks almost identical to the black line, which is with all of them. And then I also removed a whole bunch of them, points 3 to 19, and they're little gray lines, which you barely see because they look almost the same. However, if you remove point 1, then you get a completely different curve, the red curve, which you can see below there. So now if we compare these, the models, if we take the complete model, you look at the adjusted R squared, it's 0.54, reasonable. And if you look at the beta 1 coefficient and the standard error of it, you see that it's statistically significant if it's a valid model. And so therefore you would apparently have a decent regression. However, if you drop 0.1, the red point, your adjusted R squared goes to essentially 0. And if you look at the standard error of the beta 1 coefficient, you see that basically the beta 1 point, the beta 1 is 0, which means that the simple mean would be as reasonable an estimate of chlorophyll A as a function of error. In other words, what this is saying is that 0.1 basically is determining the regression. And this is a problem because you want all of your data to more or less equally determine your regression coefficients. And 0.2, you notice that it actually increases the R squared a bit, and you still have a significant regression. So 0.2 is not well fit. It has a large regression. It's away from the cloud, but it has less effect on the regression line. It does increase the R squared. It decreases the R squared. 0.1, on the other hand, which is a high leverage point, has a small residual, but the other statistics tell you that it does greatly change the slope. So the point is that it's very easy to determine if you have a valid regression by doing an analysis of the residuals. And in R, we have a simple command that gives you then these residuals plots. So it gives you first the residuals versus the fitted. You would want there basically to be a cloud of points with no pattern to it. That's the upper left-hand side. The upper lower left-hand side, sort of a similar thing. It now just takes the square root of the standardized residuals to see if your variance is homoscedastic, which would have to be. These don't look that bad, but you do see that 1 point is sort of determining things. On the upper right-hand side, we have a QQ plot, and if the residuals are normally distributed, which is one of the assumptions, you would expect the points to be on the dotted line. And finally, the residuals versus leverage, and with now the values, the Cook's distance plotted on top of it, will tell you if 1 point is having large leverage that is greatly changing the slope. So there are a whole host of things you can look at, something as simple as the ANOVA. You would want your regression to explain more of the sum of squares than the residuals, as it does with all of the points. But if you remove 1 point, which is the second ANOVA here, you see that basically the regression explains very little of the variance and that most of the variance is in the residuals. And you could also just look at the F here. And there's a whole host of plots that you could do to evaluate this. Well, in this case, if you simply did a log transform, you would start to get some better results. So in summary, I'm just saying that there are tools that are available to identify problems with linear regressions. And although I talked about this in terms of dropping points, that's not what I'm saying. You can't just drop data, but it's just a way to show how individual values can have effect to regression. So I would suggest then that diagnostic analysis be published in papers. And when you're reading papers or evaluating papers, you should take a look at these to see if the models have been properly fit. And just to show, this is in R. This is all the code it takes to do a simple linear regression and then to do the proper evaluation of it. Okay, so thank you. That's my presentation.
If there are any questions for Conrad, we have the mic in the center. Okay, can you hear me okay, Conrad?
Beg pardon?
You can hear us okay, is that right?
Yes.
You can hear us? Yep.
Yes,
so I have a question. So you mentioned reviewing, paying attention to these issues of understanding the assumptions of linear regression in terms of research activities and reviewing. But something that struck me was in the education sector. So I think my guess, looking at this, is that one reason why this kind of problem happens is that we sort of learn linear regression as students, get the basic gist, and then think this is very simple. We don't have to do anything beyond fitting and looking for the R squared. So do you think this is something that needs to be taught in a different way, or maybe talks like this at conferences are good? Do you have any thoughts on that?
Yes, and you've exactly identified the problem, because we learn it in Stats 101, and then with simple examples typically, and people just use it. And I don't think people are aware of these assumptions. I teach a data analysis class, a graduate class, and we actually spend, 3 weeks on regression and going through all of this. I don't know where it should be taught, but it seems to me, because it's so widely used, even when you're doing more advanced, simple things like when people look at the trend of Arctic sea ice, they draw a line through it because it's greatly decreasing, but that line basically is poorly fit and doesn't explain the decrease in the Arctic sea ice, those kinds of things. So I don't know where it would be put in, but yeah, it does, I think, need to be put into our curriculum.
Great. I think there's no other questions at the moment, so thank you very much, Conrad. And our next speaker will be Hamid Reza Mwasami. Thanks again, Conrad.
PDF. So.
Yeah, I'm just trying to find how to make it.
So do this.
Is this good? That's good.
Yeah, that's good. Hello, everyone. My name is Hamid Reza, but everyone just call me Hamid. So I'm a PhD student at McMaster University, Department of Mathematics and Statistics. I'm under the supervision of Dr. Nicholas Kevlahan. And today I talk about adaptive wavelet data assimilation. So four-dimensional variational data assimilation has been extensively used in climate, ocean, atmospheric numerical predictions, and we have focused on that in this study. We make it efficient with multi-grid, combined with adaptive wavelet collocation methods, and we check the limitations and advantages of using this technique, and also we compare it with conjugate gradient. So as you already know, data assimilation is the process of optimally incorporating discrete measurements into numerical techniques, which are usually in the form of partial differential equations or PDEs, to improve the state simulations. So in the variational case, we solve an optimization problem. We minimize the distance between the observation vector here, as you see, and the model simulation. And so we take the gradient to find the initial state U0, but this optimization problem is, as I mentioned, is constrained to a PDE. Here the PDE is that M, curly M, which involves the state, the physical model in space and time. And for computing the gradient, we need to run it forward in time and space, compute the differences between the observations and the simulations, and then we apply something called the adjoint model, which is derived from the forward model, but it is evolved backward in time, and that gives us the gradient equation. When the PDE is nonlinear, the problem is non-convex, and there is an efficient way to solve that, which is called incremental 4D var. In the incremental 4D var, we work on the increment of the full state delta U, as you see at the top, and that is evolved with the linearized version of the nonlinear PDE that we usually have. And we define an outer loop, inner loop system. In the outer loop, the nonlinear model is evolved. We compute the differences between the observations. And then in the inner loop, we have a nice quadratic convex problem because we are solving for the increment. People usually solve it with gradient descent. As you see at the top left, it's a gradient equation. They're in the rectangle at top left. But we are solving it in a different way. We take one more gradient, and that's the Hessian psi at the top right. And then finally, by writing the Taylor expansion and computing an optimal point, at the bottom right, we will see a linear system equation. The Hessian times the increment at the initial time step is equal to the minus of the gradient at increment equal to 0. So this is a linear system that we focus on in this study, and we try to solve it efficiently with multigrid and adaptive wavelet methods. It is a classical AUF, but it is a temporal problem. So here I compare the standard multigrid with the wavelet multigrid that we have developed in this study. The thing is that, so what is the general idea of the multigrid? The high frequency errors can be removed very fast with standard, iterative solvers like Jacobi, Gauss-Seidel, but the low frequency errors are not like that. So, but if we restrict them to the coarse scale, they will be acted like high frequency error, and they can be removed fast at coarser scales. So we have a multi-scale structure. As you see that V at the right, we have a V cycle. We do the couple of iterations at each scale, down restricting up to the coarsest scale. We use an exact solver at the coarsest scale, optimize it, and then we restrict back to the fine scale. So we solve this V cycle and we repeat it until convergence. But what we did is to change the restriction the restriction and prolongation operators of the standard multigrid to wavelet multigrid, as you see in the bottom, in order to make it adaptive. So it works in a way that when we coarsening the grid, at the grid points that we remove, at those positions, we compute wavelet coefficients, and then the wavelet coefficients which are above a threshold, the grid points associated to them are the adaptive grid. We solve the problem on the adaptive grid, and then on the special part of the region which is adaptive, and then we interpolate to the rest. In this way, we achieve efficiency. Here is a comparison of even the non-adaptive wavelet with a standard multigrid. And as you see in the table, for example, if we compare the first two rows, we see that they work exactly the same. So these restriction operators changing does not change anything. And that shows that adaptivity could lead to a significantly faster method, because this is just non-adaptive. We have another comparison here, full multigrid with the recycle. So in the full multigrid, we start at the coarsest level instead of fine, and we solve exactly at the coarsest scale, and then we prolong to one finer scale, the V cycle, a small V cycle, and then one finer, until reaching the biggest V cycle. But in this case, we have a much better initial value as the starting of the biggest V cycle, and that way it is much faster. As you see in the table, it's about 3 times faster for this simple PDE problem. And here is the results of the adaptivity. I haven't shown you the data assimilation yet, it's just PDE, but as you see, that figure at the right is the multi-scale grid that we have. The coarsest scale is at the bottom, the finest scale is at top. The red part is the adaptive region. which at each scale we do the computations, and then we prolong to the rest. And you see lots of information about the different masks of the grid that we use and how we have incorporated into the V-cycle. I don't go to those details, but one thing which is important here is that adaptivity does not change the number of optimal iterations of the V-cycle at each scale. And that's why it is very effective, useful. And here is the data assimilation, but at this slide, just for a linear PDE advection equation, you see at the top right. So the error covariance matrix of the data assimilation, it has an input called correlation length scale L, which is very effective in distributing the effect of the observations in the space. But that's very effective on our solver. Sometimes it needs to be big value in order to get a high accuracy. But as you see in the table, it highly increases the condition number of the Hessian, which means our solver would be too slow and sometimes it does not converge. So here we need to compromise between accuracy and efficiency and to choose a value in between sometimes. It's the same story for the accuracy of the observations. As you see at the table in the bottom, the table, the first column is the standard deviation of the observation values. As it is lower, which means the observation is more exact, the condition number of the Hessian is higher. Again, it's harder to converge and it's slower. And again, we need a compromise between accuracy and efficiency. We don't want to exactly catch those values because the problem becomes very non-smooth. So this is the results that we get for the linear system. Here I want to show you, so the adaptivity works a couple of iterations for the V-cycle at each scale. But here I want to compare two different ways of solving this problem. One is that, as you see at the top left, so at the left, we have two ways to compute psi times u. We can compute directly element-wise, or we can first compute the Hessian psi as a matrix and then multiply it to the Hessian. That makes it different, fundamentally, the approach that we choose for adaptivity. When the psi is computed as a matrix, all those PDEs are incorporated into the Hessian and the time is implicit. So there is no time, and then we find the adaptivity based on the right-hand side F, which turned out it works very well. The other way is that we use those PDEs, adjoint PDE, forward PDE, going forward in time, backward in time, computing psi times u directly as a subroutine. But here we have time, and the adaptive grid needs to be updated in time. So that's a big difference. But sometimes we cannot, so maybe we can say that so the other version, which the grid is fixed, and from the right-hand side is better, but it does not work always. We cannot always find the adaptive region from the right-hand side, especially when the PDE is nonlinear. Oh. And here is the non-adaptive wavelet full multi-grid result for solving incremental 4D var. So here is the problem is non-convex because we have a nonlinear PDE. And you see that the couple of iterations for the V cycles in the inner loop, and those iterations that you see at the first row are the number of outer loop iterations. Just 6 iterations was enough. But the problem is that multi-grid does not always work, especially when the problem is not elliptic. That's an important limitation because although almost always the data assimilation problem is elliptic, but when we do preconditioning, it removes the ellipticity. And as you see, we see the criteria of the elliptic system that small eigenvalues corresponds to larger scales. We have an equation that is small at larger scales and close to 1 at smaller scales. So the first row of the figure, as you see, is the non-preconditioned case, which shows that the problem is elliptic. But the second version, which we do the preconditioning, then ellipticity has been removed. So we cannot do preconditioning. And it is an important limitation in multigrid. We have to be careful, although it's very fast. So in the cases that multigrid does not work, we can solve this problem with conjugate gradient, of course, but when the condition number is high, like this problem that we see here, the number of iterations at the inner loop are high, as we see here. And here is a comparison of all the techniques that we used here. So for the linear version of solving that linear system, when the PDE is linear, almost everything works. In the nonlinear PDE, when we're solving the incremental for the var, there are some challenges, especially when in the multigrid case, we want to solve the problem in matrix form. As I mentioned, we cannot just simply find the adaptive grid from the right-hand side, and we need to solve it element-wise and update the adaptive grid in time. And in the conjugate gradient, I show you already the results of non-adaptive, and this adaptivity in time is an ongoing project, and hopefully soon I can finalize that part. We also have just started another project solving exactly the same equation using machine learning, more specifically Fourier neural operators, to somehow find an approximation of the inverse of the Hessian. When we can inverse it in a efficient way, we can simply solve that problem easily. Thank you.
Any questions for Amra? Well, I have a question.
Sure.
So I just had a couple questions. I'll just ask them all at once, and you can go through them. So one thing I wasn't sure about was, so the new adaptive data assimilation method is the idea that is the main idea for speed up of computation time, where we're hoping to get the same answer as previous but faster. And then following up on that is the computation time a serious obstacle for these types of data assimilation techniques? And could you speculate, I don't know if the research is at this stage, but for sort of state-of-the-art applications like data assimilation, weather forecasting, et cetera, what kinds of speed ups, maybe in terms of percent or something like that, could this method potentially give?
So the main idea is the adaptivity, the computational time to reduce that, and that's very important in 4D var, because to get one iteration of the gradient, we need to go all the way forward in time and all the time step backward in time. So we need to do that just to compute one gradient. And so let's assume that we are doing the data assimilation for real-time atmospheric, and so we have a time window, and we need to finalize it before starting the next time window. So the efficiency is the core here, and so the idea of the wavelets is that we look at each scale. We consider the grid points which is related to the localized structures related to that scale. So if we don't need more grid points at some points, then we can restrict it and coarsening to the next scale, and that covers that. So that's the idea. Multigrid by itself is fast, but we add even more efficiency on that by adaptivity.
Great, thanks.
You're welcome.
Our next speaker is Benush Raknaldini, who's going to speak about machine learning for water temperature prediction.
Change the slide like this, right?
I think you can change it with, I just did.
There we go. This is the back, right?
Yeah, I think it's good.
Thank you. Hi, everyone. My name is Benush. I'm coming a background of climatology and currently doing a Master of Science in Natural Resources and Environmental Studies, and also working as a research assistant in hydroclimatic informatic labs at University of Northern British Columbia. Today, I'm here to present some finding of an ongoing research, which is a collaborative research between UNBC, my university, and BC Ministry of Forests, and Tricco Environmental. And the study is titled as the use of a statistical machine learning and semi-empirical lump model to predict to develop a water temperature prediction system. This is a quick overview of the slide that I'll go over the background of the study, the objective, the methodology that we used, some key results, and then wrap up with a summary of slides. So why freshwater temperature is important? Because most fish are ectothermic, meaning that their body temperature relies on the water temperature that they are surrounding them. Meaning if water temperature increases for any reason, it can stress or even kill the fish. It can stress their movement, their migration, their distribution, feeding, or even reproduction. So it is important to us to know how the water temperature is varying and is changing in different type of water bodies. So also there is different factors which are affecting water temperature. For example, the climate change is one of the most important factor in this 21st century. And we know that the climate change in Canada is changing so fast, and according to the Canada's climate change report in 2019, from 1948 to 2016, the annual average increased by 1.7 degree, and even in northern Canada, it increases to 2.3 degrees Celsius, which is almost 3 times faster than the average of the world. And also the warmest season was like the warmest, the warming was happening in the winter in the same region, especially in the northern BC, Alberta, Yukon, Northwest Territories, where sometimes the temperature, the average temperature is increasing to 4 to 6 degrees, which is a real disaster. So considering this increasing trend in air temperature, for sure, we will have increasing water temperature. There's a study by Islamatol in 2019 when they look at the impact of climate change on water temperature in Fraser River Basin, where they found out that during the same time, from 1950 to 2015, the summer temperature also increased by 1 degree. This is only 1 degree in water temperature, but the effect is that the number of days where the temperature exceeded 20 degrees, which is the stress thresholds for salmon, almost has doubled. So not only salmon, there are other. Sorry, I think. Yep. So not only is salmon, there are other species which are affected and affecting by this increasing temperature. For example, there's a study by Fish and Wildlife Compensation Program in 2017 that they look at this temperature increase in Upper Peace River Basin in northern BC, where they found that there are 2 species, bull trout and Arctic lady, which are the temperature is a limiting factor for them. So considering this increasing trend, especially in northern BC, and then the issue which the aquatic species are under the stress of this increasing temperature in water, so we decided to develop a water temperature prediction system using some modeling which are in the field people are using for the research. So to do this, we focus on 5 study areas in northern BC, which includes a variety of water bodies, like the map of A and B are 2 lake study, which are the natural lakes, Ackling Lake and B is Fraser Lake, and then we choose 2 river body, which are Parsnip River C, and then Upper Fraser River, which is D, and then 1 site on a reservoir, which is which is Lost Cabin Creek at Williston Reservoir in northern BC. So we wanted to look at the application of different models in different type of water bodies where there are sensitive species which are living there. So for the modeling purpose, we selected 2 statistical models, which are MLR, multiple linear regression, which assumes that there is a linear relationship between predictors and output, which is the water temperature in our case, and also a generalized additive model, which is extension of the multiple linear regression, but it uses some smoothing function to take care of the nonlinear relationship between predictors and output. And also for the machine learning, we use the random forest, which is a model that make different type of trees using a random subset of data and also a random subset of predictors, and makes different prediction, and each trees make different prediction. At the end, it averages the prediction of all of these trees to make the final prediction. And also we use the artificial neural network, which is do the prediction in a kind of black box, but it's inspired with human brain and structured with an input layer, where you introduce your input, and then there are some hidden layer in the middle where it includes some neurons where the data will be processed and then make the prediction and send to the output layer. So for empirical models, we use to model air-to stream, which is specialized for predicting water temperature in river and stream, and air-to-water, which is specialized to predict water temperature in lentic bodies, lake and reservoir. So this model are a very simplified model, which they simplify the heat budget in the water bodies, and they are very limited in for the input. So like for the air-to-stream, it only needs air temperature, water temperature, and discharge, and air-to-water will only rely on air temperature and surface water temperature. So here the study framework, where we got the hydrometric data, especially water level, water temperature, and discharge from water survey of Canada. And for metallurgical data, we use the NASA Power, which is an online platform, freely accessible. And then for the statistical and machine learning models, we use some potential input, which are air temperature, water temperature, relative humidity, wind speed, precipitation, and solar radiation, day of the year, to take care of seasonality, and also discharge for river. And instead of discharge, for the lakeside, we use the water level. So as I mentioned, air-to-stream and air-to-water, which they have some their special input. And then for the training or the calibration of model, we use 70% of data, and the rest of 30% we used for calibration, for validation and testing. So at the end, we predict the water temperature, all of these models, and compare them, and pick two top performer of these models, and develop a water temperature prediction system to be trained over the historical data and predict water temperature for 2023 and 2024 without relying on observation data. So here's a portion of data that we use for calibration and validation for these sites, which is the validation period was up to 2022, except for the reservoir, where we had some limitation. There was a gap in data from 2007 to 2022. So this slide is showing an overview of the performance of all of these models. If I could use the pointer, or maybe I can use, sorry. Yeah. Yeah, I think so. Sorry, yeah, I think. Oh, it's not showing. Okay, sorry for that. So the first column is showing the MLR model in different site. The second column is the GAM model. The third is random forest. Fourth is an artificial neural network, and the last one is empirical models. So first row of the two first row are the river side in order: Parsnip River, Upper Fraser River. The third row is reservoir, and the last one is Ashley Lake. So different models showing kind of where all of the model were able to capture the overall seasonal temperature, because this is only showing during the summer of May 1st to September 30. And then all of the models were able to capture the overall seasonal temperature, but they had some limitation in taking care of the daily variation in sometimes. So, for example, the MLR model, sorry, I need to tell that the black line is showing the observation, the red line is the prediction by the model, the blue bar are the cold bias of the model, and the orange bar are the warm bias. So between these different models in our analysis, GAN model and artificial neural network were the best, and for most of the site, except for the reservoir, where the random forest and GAN model work better. So there are some limitations in some models. If you can see, for example, in third and fourth rows, which is they are the lakes. The last one are air to water for the Atlin Lake and the reservoir, where the model were very smooth. It was capturing the overall trend, was not able to capture any daily variation. So to look at why is the reason, we look at another the application of air to water in another slide, where we look at the Fraser Lake. So the reason that we chose the Fraser Lake, it was that all of these sites, Atlin Lake and a reservoir, where the water temperature was recorded by Water Survey of Canada. They had a special way of recording temperature by attaching the water temperature sensor to the water level. So it was kind of the temperature sometimes was due to the fluctuation in the lakes, the water level in the lake. Sometimes the water temperature was recorded at the surface. Sometimes, for example, in the reservoir, it was recorded from 2 to 18 meters in the depth. So it was the reason that the model was not able to capture daily variation, because the water temperature was not correlated with air temperature. And because this model, the only input that it takes is air temperature and water temperature for sure, it is a limitation for the model, and it reduced its accuracy. So, but for the Fraser Lake, where they used the sensor which was attached to a buoy at the surface, it was able to capture all the daily variation. So it means that it's not fine to always judge the model based on what we see in their application. Yeah, thank you. It's important to look at the water quality, the data quality. And analysis shows that in the case of where the air to water was not able to capture daily variation, statistical and machine learning was more able to capture this daily variation. It's because it's taking more of the variables, so it's reduced the sensitivity of the models to the water temperature data. So using top two performer of the models, we developed the water temperature prediction system. So as you see here, and we trained over to all of the historical data that we have up to 2022, predicted water temperature for 2023 and 2024 during the warm season of May to October. So the prediction is daily, and then as you can see, the black line is observation, red line is prediction, where the water temperature prediction system was able to capture both overall seasonal temperature and daily variation. There is a gap for the Atlin Lake, and as I mentioned before, it's because kind of the water temperature is not as much good as it should be, because the water temperature is not recorded at the surface, and then it might be the reason. But it still is a research model, so we are trying to increase its accuracy by including more variable in the future, or even more, and we would like to try it to more different site in BC, or perhaps in other water bodies in Canada, to make sure it's general applicability. So to summarize, we compare different type of models, and then on different type of water bodies, and develop a water temperature prediction system. And then the results show that the model can be reliable for prediction without relying on observed water temperature. And then we found that the air to water is so sensitive in terms of water temperature to be correlated with air temperature. And then in case if we do not have a reliable water temperature, it's better to use machine learning models. And then moving forward, as I mentioned, we would like to try it and make sure that this water temperature prediction system is reliable to be used to other parts of Canada. And I would like to acknowledge that this research is funded by Fish and Wildlife Compensation Program, and then the Natural Science Engineering Research Council of Canada. And then here is and I would like to thank the data resources that I use for this study. And thank you.
So we have time for about one quick question, if anyone has a question. Yeah, you can use the mic, please.
Thank you very much for your great presentation. It's very interesting in comparison of the GAN model and other statistical model with the machine learning algorithm. I just have a recommendation for your future studies. You can incorporate also cyclic splines for better capture the seasonality in your modeling. Perhaps it could improve your modeling as well. Thank you.
Thank you so much, for sure.
Thanks, again. Our next speaker will be Jeff Sapiri.
Sorry, if you please tell me how can I share it?
Hi, Jeff, can you hear me?
Yes, yes, I can hear you.
We can't see your presentation yet.
Okay. I don't know. Can you see it now? No? Oh my God.
Just bear with us for a moment.
Oh, I think it is this now. Now, can you see it?
Not quite yet, Jeff. Just I think we're working on it. I think we're close. Just hold on a minute.
Excuse me, I cannot share. I will try to share it. I cannot.
Can you start over?
Can you try to reshare maybe stop sharing your presentation, then reshare it, please?
Sure. I
showing.
start sharing.
Jennifer, can you start over?
And going to Bihlo. Now I share it. I can see it in the down of my pages. I'm very sorry.
Sorry, Jeff, we're just trying to figure this out.
I can see here. I can see in the left side of the screen my files, but I don't know. I will try to share it again. I stop share and let me.
Jep, can you please log out and log in again, because I
Log out and log in.
I can see one computer, but I think you are not. We cannot see even your picture.
Okay, I go out. I'm going out.
And make sure you turn on your camera. Sorry. Jep.
Oh no, you should see it. Yes.
Yes, we can see it now. Just hold on.
Okay. Sorry for. Okay, I'm very sorry. Okay, excuse me, the audience. Good morning. This is that my article is the temperature prediction of the Pincher Creek region using an ANFIS, adapted neurofuzzy interface system, a case study, and we are working on the.
Sorry, Jeff. Could you just pause 1 second? Could you please go to presentation mode to make your presentation full screen?
Presentation mode. Yes. Now, is it okay?
We were having this issue yesterday. When you go into your shared screen mode, are you sharing the window or are you sharing the entire screen?
Sharing the window.
Can you please stop sharing your screen and then do share screen again and then do share entire window, and then we'll be able to see your full presentation.
Now I share the entire screen. Now can you see it? Can you see the?
Yes.
No, can you see it?
Yeah, we can see your presentation,
okay.
but it's not full screen yet. If you could make it full screen.
Not full screen.
No, okay, it's not possible.
Now can you see the full screen?
Is this as good as we can do? Okay, we're just going to go like this, Jeff.
Is it okay?
You can. So you can go ahead.
Okay. This is the forecast hourly air temperature using an ANFIS system in the area named Pincher Creek in the southern Alberta. Our data period as 2011 to 2024, hourly 3 hours for each measurement. The variable we use the temperature and relative humidity for this model, but in future, of course, we use the other variables. The data size that we have is 110,000 records almost after cleaning. Around 70% of them for training, 30% for testing, and 1,000 for extrapolation. The inputs features are temperature and relative humidity for each 3 hours. The output target is temperature at the next hour. We use the evolution metrics RMSE, MIE, and R2. And the performance training RMSE is 1.3, for testing is 1.29, and for extrapolation is 1 to 26. And R2 for training is 0.98, 99 almost. For testing is 0.99. And for extrapolation is 0.96. The ANFIS accurately models short-term temperature using hybrid AI techniques. The promising model for local forecasting. Future works can include more variables. This is the area. This is the Pincher Creek area. You can see here at the right side in the domain of the Rocky Mountains. Excuse me, and this is the graphs that I drove for that special area. You can see the Pincher Creek station here, the Pincher Creek climatology, the Pincher Creek station, the Pincher Creek climatology station, the Broken item, and the Beaver Mines. And this is very interesting that in Beaver Mines we had many points compared to the Pincher Creek. Pincher Creek is in the domain of the Old Man Valley, Old Man River Valley. The geographic feature is natural wind corridor here, mountain included air currents, and high variability topography. It is the area is a cold and temperate in the Köppen climate classification. The average temperature is around 4.1 centigrade, and the annual precipitation is 613 millimeters for annual. The wind condition frequently Chinook winds from 50 to 90 kilometers per hour triggered about temperature changes. The extreme example is the 1962 from 19 jump to the plus 22 in 1 hour due to the Chinook effect. The forecasting channels is rapid temperature humidity shifts, complex wind interaction, and nonlinear atmospheric behavior. Why this area? You can see that the area that I show it here is the almost the area of the wind farms. It is ideal for testing advanced model like ANFIS and real-world scenario for dynamic data-driven forecasting. So, excuse me, I try to don't repeat something. So just the important part of the data was collected from the Pincher Creek Weather Station in the southern Alberta 2011 to 2024. And we used two main variables collected, temperature and relative humidity. After cleaning, around 110,000 for the data. And the z-square normalization, it means that means is 0 and standard deviation is 1. The outlinear handling, outlinears removed to reduce noise and enhance accuracy, and the input structure for based on temporal autocorrelation, the input temperature and relative humidity as T minus 3 minus 2 and T minus 1. So for the testing, for the testing, we reach for the training, we reach to the T, the local time. But for the testing, we use T minus 2, T minus 1, and to T to reach the T plus 1. A prediction target is temperature at time T, and the purpose of design is capture temporal dependencies for improved short-term forecasting accuracy. You can see here that we have 6 inputs, the 3 of them temperature for 3 continuous step time, and 3 of them are relative humidity for 3 continuous, the same 3 continuous step times. They are going to the input layer for membership function, from them to the ruler layer for fuzzy interface, then from the learning layer for hybrid optimization, and from them to output temperature at T, it means that next hour. So this is the schemes, the schemes of the board. So you can see here we have 6 inputs. We have 6 inputs. These 6 inputs, they are for this. They are going for T minus 2, T minus 1, and T for temperature, and so for relative humidity. 6 inputs, and for nonlinear, it is much better to use the genotype FIS. So the subtractive clustering for generating closure rules and predict temperature at T plus 1 next hour. Capture temporal dependencies between recent values and future temperature. Here you can see the different layers here. We have the input layer. We have six different kind of data, three temperature and three relative humidity for each of them for three continuous times. Then we categorize them in three groups: low, medium, and high. It means that now we have six categories. It means that temperature low, temperature medium, temperature high, and so relative humidity low, medium, and high. Then constructs fuzzy with if then else rule for the rule layers using fuzzification inputs, uh, uh, some with and logics, and the number of rules depends on the combination of fuzzy sets from input variables. Then we normalize layer the strength of the each rules to ensure fair proportional contribution to final results. In the output layer, we aggregate normal as rules output to produce the final predicted temperature at T plus 1. This is the model's ultimate forecast output. Then here you can see the regression of these data. We have six different data, and we have four membership for each of them. So for input data, we have the temperature and relative humidity for these three times. Output is that temperature for 3 plus 1. The membership function type, the Gaussian highlights in yellow, chosen for smooth differently and gradient-based learning suitability. And the x-axis of each plot is the represent the numeric values of the input variable, and y-axis shows the degrees of the membership from 0 to 1. The plot layout, the column, we have six column, which means six data input that we have, and the rows are the membership that have. The red line that is plotted indicates the mean, the center of the each Gaussian membership function. The box placed right side of the figure, this part, shows training error distribution. Narrower spread indicates high accuracy and low training error. So it is significant that proper design and spacing of function ensure good input space coverage, effective rule generation, and enhance predict performance. So, for model performance summary, the ANFIS forecasting results. This slide shows how well the ANFIS model predict temperature using past temperature and humidity values. It uses data from the last 3 hours to guess the temperature for the next hour. The model performs very well through the training, testing, and even future data. The errors are small and mostly close to zero, which means the prediction are accurate. Even when the predicting beyond the training time range, the model still works well. A regression check shows the predict and reveal values and very close proving the model understand the patterns in the weather data. So in the interpretation of results, this slide highlights how well the ANFIS model performs in forecasting short-term temperature, even in areas with complex and changing weather like in you. It is in the domain of the Rocky Mountains. Rocky Mountains is from northwest to southeast. But in this area, Pincher Creek, in the mesoscale, it is from northeast to the southwest, and it is the Old Man River Valley that conducted the winds. The model showed very high accuracy, R to above 0.98 during training and testing, and still performed well when predicting new unseen data, showing it can generalize beyond what it has learned. By using temperature and humidity from the past 3 hours, the model captured important time-based patterns. Errors, uh, errors here, excuse me, sorry. Uh, uh, some, yes, model performance. Yes, The strength and limitation of the ANFIS forecasting model, you can see that we have the advantages of the ANFIS model and limitation and challenges of the ANFIS model. The advantages of the ANFIS model is hybrid learning, interpretability, stability, efficiency, and extrapolation flexibility. And the limitation and challenge of the ANFIS model are limited input diversity, short-term focus, and parameter sensitivity. So, recommendation for future returns, expand input variables. And as I told you that we just use the relative humidity and temperature, but in future we add wind speed, pressure, and even solar radiation to improve prediction under complex conditions. Evaluate longer forecast horizon, test performance for daily, monthly forecast to validate broader application potential, optimize parameters automatically, uh, and test in the other regions. It is very important that we should test this model in the other regions, and hybrid model integration, combine ANFIS with DNN or ARIMA for enhanced performance in a specialized forecasting test. In conclusion, this study shows that ANFIS is a strong and reliable tool for short-term temperature forecasting, especially in places with rapidly changing weather like Pincher Creek. The model not only predict accuracy but also explain its reasoning through the clear fuzzy rules, making it easier to understand how decisions are made. By using recent temperature and humidity data, ANFIS captures important patterns to forecast the next hour's temperature. It worked well across different data sets, including unseen future data, which shows its ability to generalize. With further improvements, such as adding more weather variables or testing in other locations, ANFIS could become a widely useful model for practical weather forecasting. And thank you for your listening.
Any questions for Jeff? Hi, Jeff. So I have a question. So I was interested in your model architecture, which used this grouping, I think, inputs into these membership groups. What was the motivation for using this kind of fuzzy setup compared to, say, just a traditional neural network where the inputs are just taken as the values?
ANFIS combines, thank you, this is for your question. ANFIS combines neural networks and fuzzy logics to learn and handle complex weather patterns. In Pincher Creek, it predicts temperature more accurate than traditional methods by using data like humidity, wind, and sunlight.
And just one short just comment is that given the Chinook example, I thought it was obviously a good first step, but I thought it was a bit surprising that wind wasn't included in the model. You mentioned incorporating wind speed into future versions. I think wind direction also might be very important.
Yes, of course.
Do you have a question? Yeah, yeah, we have time. We have one more question. Can you take the mic? Get a bit closer, please.
How does the ANFIS enhance the temperature prediction accuracy in Pinch Creek area compared to traditional statistical modeling?
Did you hear that question, Jeff?
Yeah, I think yes. I think in the Pincher Creek area, when we compare the ANFIS could show the best result compared to the traditional models. And I'm pretty sure that by adding humidity, by adding the wind speed and direction, and sunlight radiation, we reach to the better, much better answer than the traditional model.
Okay, great. Thank you. So our next speaker is going to be Zhenhua Li, who's going to talk about bias correction.
He will not be better. He's on another.
Okay. Okay, well, should we just break early for lunch then, I guess? Or?
Yes.
Okay, actually, our last speaker is under the weather and won't be presenting. So given that this is the last talk before the lunch break, we'll just break early for lunch. And we'll be back at 1:30 for the second part of the session with lots of interesting talks. Great. So thanks for your participation this morning, and I'll see you this afternoon. Sorry? Oh, yes, it's all, you can, yeah, it's fine. Okay. Yeah, actually, that happens. Yeah. Thanks. Oh. Yes, I'm going to be the, I'm excellent. Great. It's great when presenters are here because we have less technical problems. That's great. That's great. Did you get a chance to go to the meteorology session yesterday? Yeah. I couldn't make it for actually. I was sick. It was sick. But was it a good session? Yeah, of course. Yeah, well, yeah, just yesterday. I mean, yesterday, right? Yeah. Wonderful. Well, hopefully we have, I don't know how many we have. I guess it will be a mix of virtual and in person, but that's great. Yeah, I had that problem. Oh, I don't know. Maybe, actually, maybe ask, he might be the one to know that. Adapting to the audience. Hi. Yes. I'm going to introduce myself, Peter Taylor. Fitzgerald, sorry, I don't have my thing on. Okay. We're talking with Scott Lockman. Oh, sure. Yeah. About the potential work on thoughtful persons. Okay. Did you give a fog talk at CMOS in St. John's 2 years ago? Yeah, I was in the room. I was there. Okay. Yeah. So Scott isn't here. I don't think so. Actually, it was too bad. We weren't sure how many of the newbies were able to get out for this, but it ended up being the case that 3 of us convened this. I thought, happens to be one person. So we were Sunday guy as well. But he's the one guy. But we had 3 conveners. Oh, I was the only one. Yeah, sure.
Wait, so how to 10 pages?
It was supposed to be a
Here,
whole
you use this 10 pages?
Yes.
Which page? 10?
Yeah, so
10. No, keep going.
Yes.
Okay, this one. This one.
Yeah.
Okay.
The company does fossil gas.
Okay.
And
Oh, sure. Yeah, sure.
they see the funding. The problem is the funding has to be spent in you.
Oh, I see. Sure. That makes sense.
Most of it, yeah.
Yeah.
But we're talking about other possibilities. Terry Bullock, you know Terry Bullock?
No. What is he at mine?
Can you see?
No, he's with
Yeah,
the
this one.
company, I think it's WSP.
Okay.
They keep changing their.
I see,
their
sure,
names as they get
sure.
taken over by different groups.
Yeah.
But, no, we're very interested in, it's what
Not
we're
here.
doing with,
Yeah,
with
I-
Terry
Not
and his
here.
group.
Not here?
I'll ask Daniel.
I
Yeah.
remember what you
Then
were
we
talking about.
can plug in here. Do you have the USB?
I put it in her USB. I don't know where she's. I found her. I'll find her. So she can operate this computer, right?
Yeah.
Okay.
I'm here, but I'll be volunteering in the next session, so she can come back.
Well, this project in Fatima,
Okay.
run out of Notre Dame University by Joe Fernandez.
Yes, I
That involved field work, in the Grand Banks and on St. So we did all four of them.
Right.
Yeah, supported.
With observations.
Yeah.
Yeah.
Well, we did it as a service for the planning of the experiment. We did it every day for a couple of months for Staten Island.
Yeah, I guess that's sort of, so I don't think about fog. So
No,
my work is more turbulence related and large
Yeah.
scale. I don't really think about fog or precipitation of any kind. But I guess with fog, one of my questions for doing AI stuff is, everyone knows AI is notoriously data hungry. And I don't know. What's the general quality of fog observations? Is it pretty good? Not that good?
It's not very good. I mean,
Because I know fog is also very localized and often ephemeral, right?
it's probably less localized over the ocean than it is on land,
Sure.
where there's a lot of topographic effect. What two of my students have done at different times, with different models,